Yeah.
And then okay the recording.
Just click OK.
Just click OK. Start. Yeah, that happens. Okay. Okay, so we are extremely glad to have Professor Pratik Sharma from Indian Institute of Science, Bengaluru as our speaker today. Before I introduce Pratik, I have one thing to say. That is, when many of you came to presidency and on the day of the orientation, you were told that there are certain things at presidency that are very different from other places, which may be good or bad, and you should try to appreciate the good and try to improve the bad. So today is an example of one of those great things, that today is a holiday, but we already had this talk planned, and some of us were very interested to have this talk offline, and we informed you and all of you showed up. Also, this was just before the puja, so we had some refreshment arrangements. So we had a before the puja break, having a sort of celebration is nice. And also the fact that, I mean, originally plan was to celebrate on Wednesday, on Teachers' Day. There were some cultural things, etc. And then Thursday would be the talk and these things. But at least the fact that when we are thinking of celebration, we are thinking of having a good talk. That's one of the things that's a little bit different here, and we all appreciate that. So and this doesn't only. I mean, I should mention one thing, because this happened earlier this week. That Prithu came to our elective class, which he's not really taking for credit, but he came and he gave an excellent presentation on motion of stars in the galactic potential, including codes and videos, and he's just auditing the code. So that kind of things are not very common. You may think that these are common, but this is not. And I appreciate that, because I'm doing this for, well,
11,
more than a decade now. So thank you all for coming, and thank you for being part of all these activities. So now coming to Pratik's introduction, Pratik did his undergrad at the Engineering Physics Department at IIT Bombay. That department produces regularly very good physicists, very good researchers, and including astronomers. There have been previous speakers who were from there. So they are definitely doing something great. And then Pratik went to Princeton in the plasma physics division for his PhD. And then after his PhD, went to UC Berkeley for his postdoc. And then he also got the Einstein Fellowship, which is one of the most prestigious postdoctoral fellowship in the world. And with that, he stayed on in Berkeley for a few more years, and then came back and became a faculty member at Indian Institute of Science since then. There have been, as you know, there have been former students of the astrophysics departments who became PhD students with Pratik and did work. And Pratik has received numerous awards. I'm not going to list them. Includes I think Swarna Jayanti Fellowship and Humboldt Fellowship and Booty Foundation Fellowship for excellent work in plasma physics. And today Pratik will talk about the neighborhood of galaxies. So Pratik, please.
Yeah, thanks a lot, Yeah, thank you for the nice introduction and for hosting me here. I wanted to come here. I've never been to presidency, and I've heard so much about it. Also from my students, especially Alankar Datta, who is a BSc student here and an integrated PhD student at IISc. And anyway, so this place is in the science folklore of India. So it's a great honor and a pleasure for me to visit this place. So Somdev took me for a little round of the university or the campus, and I was really happy to hear about some of the historic things. So anyway, I also must say that this is indeed a unique place. I was visiting Saha Institute for Nuclear Physics as a colloquial speaker, but there I really did not have much of an interaction with students, which I really wanted to have. Somehow the students are not as free. So I think, it's not a negative thing about a vibrant place that the students have to be like your colleagues. They need not like follow all your orders, and sometimes they can have better ideas. So I really like the atmosphere that you guys have created here, and you know being able to differ from your boss, and showing something that can work better, and the bosses being happy with that is a very good thing.
Yes. What about our students? Apart from all the things that I said, I think they collaborate with each other a lot, and that's what we
No,
really
that's very, very good.
encourage and love. That
And
they-
I think that's like a good
Yeah.
beginning to the research experience in the research world. So the talk is, after hearing the introductions, I think for some of you this may be extremely trivial, but let's just keep it somewhat informal. You stop me wherever you have problems or if something is not clear. So that should be totally fine with me. So this is the topic that I'm going to talk about: the massive atmospheres around galaxies. This is something that I'm really very excited about right now. I worked on different things in past, but this is all aspects of this problem are my current focus. So let's get started. Of course, all of you know this. The universe started with the Big Bang, and there was an early epoch when everything was opaque. And then you have the CMB, the Dark Ages, the first stars and the first black hole quasars, and blah, blah. This I do not really need to mention here. JWS is detecting galaxies here, the very first galaxies in the universe. We are here. And of course, all of you know that the fluctuations, the tiny fluctuations that you see in the cosmic microwave background is responsible for creating all the structure around us, the IGM, the galaxies, and so on. So this is sort of the big picture, and I'm sure everyone here knows it. So this is just a simulation simulation which sort of tries to look at formation of structure in the universe in that context, in the context of lambda CDM model of cosmology. So if you look at these, this is a dark matter only simulation. This is the famous Millennium simulation. And what you are seeing here is like a snapshot of density with time. So this is the earliest time, the next, and now. Now this is a massive cluster at redshift 0, but it started in more not so extreme situation at the beginning. The universe was much more homogeneous. Gravitational instability made these fluctuations larger and larger, and they evolved into these filaments and voids and clusters and so on. So this is sort of the context. These simulations are n-body simulations. They just have gravitational interactions between dark matter particles. It really does not matter what the particle nature of dark matter is for this purpose. Their job is just to provide gravity. Now the baryons, that's what I am most interested in. Although they are a small fraction of the matter, but that is the fraction that we can observe easily and understand. We have great deal of data on. So on large scales, the baryon to zeroth order baryons follow dark matter because that's the gravity that pulls not only dark matter but also baryons. But as you go closer to halos, they are affected by other processes, baryonic processes, like dissipative processes. For example, gas can collide with each other and can get shocked shock produces thermal energy, and that thermal energy can be lost, right? It can be lost as radiation, which leaves the system. So energy can be lost from baryonic material. So they are dissipative. And galaxy formation, which is the formation of luminous stars in these dark matter halos. So all these halos, here is the dark matter view, but these are lit by stars which form in a lot of these somewhat massive halos. And dissipation is necessary for star formation to happen, right? The gas needs to become molecular and cool a lot before gravity can compress it and make it so dense so that you can burn hydrogen at the center. Okay. So baryonic processes, dissipative processes are extremely important for galaxy formation. And not only can baryons cool, they can also get heated. So this is the feedback aspect of galaxy formation, that you have these massive black holes that can launch jets. You have supernovae that can put in 10 to the 51 erg in mechanical energy back into the gas. So it can control, it can sort of self-limit star formation. Now, radiative cooling is an extremely fundamental physical process that governs galaxy formation. This is something that people may not appreciate as much. Cooling, it's basically atomic physics, right? You have collisions, and the atoms can get excited to higher energy. Electrons in an atom can get excited to higher energy level. They de-excite, they emit radiation, and that the radiation can take away some energy, right? That's the source of cooling in optically thin gases, right? So optically thin means as soon as radiation is produced, it leaves the system at speed of light. For example, stars are not optically thin. A photon which is born at the center of the sun takes 10 to the 4 years to make its way out because it's optically thick. Okay. What we are talking about is this diffuse atmosphere around galaxies, which for in most regimes is optically thin. Now, if you have an optically thin plasma, you can actually, I don't know, have you done this in the coursework?
No,
No, not really, not really. Okay. So what you are seeing here is something called a cooling function. Okay. So if you look at the thermal energy density, if you have gas at some density and at some temperature, if the plasma is in ionization recombination equilibrium, that is, the density is high enough that ionization and recombination rates are fast, you call this plasma plasma in equilibrium, ionization equilibrium. So here is something called the cooling curve, by which we can actually characterize the cooling properties of an optically thin plasma because of emission of lines. So these are, so there are a lot of curves that you see here, and these curves correspond to different metallicities, right? So if you don't have any metals, this is the lines that you will get, right? So this is log temperature. So this is 10 to the 8 Kelvin, 10 to the 7, and so on. So you have this bump, and then you have this bump, and then you have this. Do you know what these sort of peaks are due to? So these correspond to hydrogen and helium, right? So the hydrogen becomes fully ionized after 10 to the 4th. So then if you become fully ionized, there are no electrons that can get excited from low to high levels. You totally go to continuum. So helium has a higher ionization potential. So it has, even at 10 to the 5 Kelvin, it has some probability of being in of being present. Okay. So, in fact, if you go to, so these numbers are log of metallicity. So 0 is solar metallicity. So you sort of bump up all the metals, everything from lithium onwards by the same fraction. So you get this. So you see these other peaks become prominent as the metallicity increases, and it's simple to see because you can start to have ions like oxygen, various ionization states of oxygen, and so on. So you have these things. So people have actually calculated cooling tables based on atomic physics calculations, and here they have tabulated this, and that's what we are going to use.
Solid one is the pristine gas.
This solid one is the solar metallicity. This is the nil.
It's the nil.
Nil one is the pristine. There is only hydrogen and helium. Okay. So the thing is, and this is just free. When you are about into the 7 Kelvin, even iron, which is an abundant element, gets fully ionized. So you are free emission here. So all of these collapse to a narrow line. So the point is, this region of temperature is a sweet spot for cooling of gas, of the cooling of diffuse gas, and this gets reflected in the abundance of galaxies. Galaxies do not populate halos equally, right? The very massive halos have very less stars. Like cluster halos, stellar fraction is small compared to Milky Way like halos. But even on the smaller sides, the dwarf galaxies and so on are very poor star formers. So the fundamental reason for that is atomic physics. Okay. So strong cooling picks out halos in which luminous galaxies can form. And of course, these curves are calculated from Saha's fundamental contribution, where he uses ionization, recombination, equilibrium, and says, oh, this is the fraction of, say, hydrogen or helium at this temperature or metallicity. Okay. Now, so as I said, my focus will be on baryons. So these atmospheres, the gaseous atmospheres of galaxies, we call them a circumgalactic medium or the intracluster medium. CGM normally is used for Milky Way mass halos, like 10 to the 12 solar mass halos. Intracluster medium clusters are halos which are 10 to the 14 to 10 to the 15 solar mass. That's just a convention. Cluster atmospheres are much better understood and known because they are denser. ICM is denser than CGM, generally speaking, and also hotter. So, we have X-ray telescopes like XMM and Chandra, and they have really done a very good job at mapping out, electron density, temperature, metallicity, and so on for the intracluster medium. But the CGM is extremely difficult to observe. So here is sort of the dark matter picture. If you zoom in, so this is like a cluster halo, like a mass. If you look at the light map of, say, India, clusters are sort of like a metro city, right? All the neighboring roads and so on connect to the metro city. Now, these guys, our Milky Way and so on, are more like towns. Right. There are many more towns than metro cities. So most of the population actually resides not in metros still. They are still in like mid-sized towns. So in the same sense, most stars are not in clusters. They are in like Milky Way like galaxies. So this is like a cartoon of a Milky Way. So you have this massive dark matter halo 10 to the 12 solar mass. There is a diffuse CGM, diffuse atmosphere around it. It's about 200 kiloparsec. The disk, the interstellar medium, and stellar disk is only 10-20 kiloparsec. So this is very diffuse. And most of the baryons associated with these halos, with, say, Milky Way halo, are not in this. They are not in stars or in the interstellar medium. They are actually in the diffuse atmospheres of these galaxies, which we can barely make out. So this is the missing baryon problem, the halo missing baryon problem, if you may have encountered this. The other thing is the hot gas which fills this up for Milky Way or cluster galaxies is close to the virial temperature. And for clusters, it's about 10 to the 8 Kelvin. For Milky Way, it's around about 10 to the 6 Kelvin. So here is actually the illustration of what I was just saying in words. So the x-axis here is the halo mass, characterized in terms of M500. You can just sort of think of it as mass in the total mass, which is dominated by dark matter, total mass of the halo. And these are data from stellar surveys and from X-ray modeling, X-ray observations. So what you see is that, so this is 10 to the 13 to 10 to the 15 solar mass halos. Milky Way is around here. It's not sort of shown on this plot. It's sort of somewhat lower mass. So this is group and cluster. So what you see is as you go, the halo mass decreases, the fraction of baryons in stars increases. And the fraction of baryons in gas. So this is gas, and this is not ISM gas. This is this diffuse gas, which I just said that it's easier to observe in clusters. In this we don't have Milky Way data here. This is impossible to get from Milky Way, like HALO. Now, if you add these two up, this is what you get.
That's a very good.
That's the total baryon fraction of a halo. So you see, these sort of compensate each other, and it's roughly flat as a function of halo mass beyond 10 to the 13 solar mass. Okay. So the most massive clusters are thought to be baryonically closed. That is, all the baryons associated with that patch of the universe are there in clusters, but not so for lower mass galaxies like Milky Way or dwarfs. So if you have any questions, just interrupt me. I'll be happy to take them.
So the reason that we cannot
This is the figure that
Oh, that's right. So the yeah. That will easily detect ICM gas. I mean the gas, as you said, but so for the CGM. That's because of the emission. I mean, it's very weak, or I mean.
So two things, right? So there are, right. So first of all, it is 10 to the 6 Kelvin. So that's like soft X-rays or UV. Now, second thing is the density is also smaller, and the path length is also smaller, right? So the pen I put it. So Ni, lambda, lambda P, BS. Right? This is what your surface brightness would be. So these densities are small, and the path length is small. So the whole thing is small. The other thing is, if you have 10 to the 6 Kelvin plasma, you are losing most of the, they don't really emit even in soft X-rays. So you really need a UV telescope, which was one of this, Lubor is one of the items for the next generation JWS, the successor of JWS. There's a lot of talk about the UV imager explorer being the next.
To detect this circumgalactic.
Yeah, basically to map out the IGM and CGM, all diffuse gas basically emits in UV, low redshift. So that is the thing. So, okay, so you already know about this figure. This, for some reason, this has become very famous. This is from an early review article on the CGM. So it's just a cartoon. What it shows is what comprises this galactic atmosphere. So you have things like this. This is IGM filaments. You have the intergalactic medium. You have dark matter, which is coming preferentially along certain directions, but they also bring in baryonic matter. and some of it can actually make it all the way close to the galaxy. So this is the color scheme is less metal rich because it's sort of coming from much larger scales. So it's fresh gas. Okay. Now this one, so the gas is coming in. There is star formation, and stars can sort of put energy into the CGM. It can also produce metals, right? Supernovae throw out metals produced in stellar interiors, and it sort of pollutes the CGM with metals, and also puts out energy. So this is sort of feedback and metal enrichment. So this gas, which is most of the baryons in the halo, is actually the source and sink of mass and energy to form galaxies, right? So for example, if you take Milky Way, it is forming stars at a few solar masses a year, right? Now, if suppose you say no, interstellar medium right now is what I have for producing stars. You cannot sustain that one solar mass a year for more than a giga year. So, but if you look at the star formation history of Milky Way, you see that this solar mass or more per year has been going on for almost the age of the Milky Way. So that means somehow you have to replenish it. And this replenishment comes from this diffuse phase. So it's very, very difficult to make this out, how it happens. Okay. Now, how do we observe the CGI? In fact, we also had a little discussion about this at the beginning. Now, so one of the popular ways to make out the presence of these galactic atmospheres is through something called quasar absorption lines. Okay, so this absorption line studies have been used to also detect and characterize the IGM, intergalactic medium. So wherever the gas is diffuse, low density, emission is very, very weak, right? If n is small, n squared is even smaller and it's difficult. You can actually do absorption. So this is a quasar. For the purposes of this, an AGN or a quasar is just a bright continuum source. Okay, so there's light going out from here, and some of it also comes in our direction. And if there is intervening IGM, intergalactic medium, or a galaxy which is not very far from this line of sight, the matter around this can actually absorb light from here, right? And that is what we see in, say, this Hubble Space Telescope cosmic origin spectrograph. This is one of the spectroscopes that have actually done a lot of work on low redshift, characterization of low redshift CGM. So what you see here is if this diffuse atmosphere was not there, it would all be like like a constant continuum radiation. But because of the presence of certain ions and atoms, you get these signature spectra embedded in this continuum. And from modeling this, you can actually figure out how much of various ions are present at different densities and temperatures. Okay, so that's like the basis of absorption line spectroscopy. The same technique is used for IGM as well. Okay, so some of these absorption lines are, say, due to oxygen 6, say, which is O5 plus. Right, it's a tracer of somewhat hot gas, 10 to the 5.5 Kelvin is where its peak abundance is, and it's a UV. This line is in UV and it's a doublet. Now the thing is, it's important to have doublets. Otherwise, you do not know whether it's oxygen 6 or magnesium 2 or whatever. If you have doublets, then you definitely know that this is that particular transition and it is at that redshift. Okay. I sort of see familiarity among the students.
So they have a lab where they actually find the redshift of a galaxy and they use the calculator.
Yes. So
we
these
always
are
ask
very, very
them-
important.
We always ask at the end of treatment, why do you use that?
Otherwise, there is a degeneracy, right, between redshift and the element or the ion. But with the doublet, that degeneracy is no longer there. So some of the popular, ions are Mg2, Mg plus, which is, and so on, right? So we'll actually encounter some of these. Even the sulfur doublet is a common tracer. Yeah. So, from this abundances, we can also measure abundances, right? We can actually see how much hydrogen absorption happens, how much, say, magnesium or oxygen 6 happens. So you can also get a sense of metallicity from this.
So, Pratik, one thing. So here the observer is not in this galaxy. It's coming from some
It's an
other.
intervening galaxy.
Right.
Right. So basically, the nice thing about this is our galaxy does not interfere with it because it can only be an oxygen doublet at this redshift. So there are two things. So you have to know the host galaxy of whose CGM you are intervening. So the redshift of this and the redshift of these lines have to be within few hundred kilometers per second of each other. If they are separated by large, they cannot be physically connected. Good. So even for Milky Way, people have done this. But for Milky Way, Sanskriti
Yes.
Das, your student has done a lot of this work for characterizing Milky Way's CGM in X-rays a lot, and the other wave bands. So she's doing everything on the observational front, and done a lot of work on the Milky Way CGM. But here is an intervening galaxy. So there's Gauss halos, one of the survey, which was actually looking at pairs of quasars and galaxies. So if you have a quasar and a galaxy within certain distance, then they would just sort of do this. So those will be the targets, and they will try to do this modeling. Because this is very expensive. It's not a cheap technique. So this is from the same review article. This is an image which sort of shows the distribution of temperature and density. So this is 10 to the 4, 10 to the 5, 10 to the 6 Kelvin. These are densities 10 to the minus 6 particles per centimeter cube to 100 particles per centimeter cube. Now, these are the various ions that in collisional plus photoionization equilibrium, this is the density temperature in which these various ions exist in. So for example, if the gas is at 10 to the 6 Kelvin, and if your density is 10 to the minus 5, 10 to the minus 6, the tracer that you have is oxygen 8. Okay. So these are traces of somewhat warmer or hotter gases. These are traces of cooler gas. So you can actually see sulfur 2, carbon 2, iron 2, and so on. This is oxygen 6 that I mentioned. Now, this instead actually shows you various lines corresponding to some of these ions. And the x-axis here is redshift, right? So if your redshift 0, that is in the Milky Way neighborhood, almost all these transitions occur below 3,300 angstrom, which is in UV. So you need space spectroscopes in order to do a lot of CGM science at redshift 0. But if you go to redshift 2 and 3, a lot of these come in optical, and you can do it with ground-based telescopes. So in fact, somewhat counterintuitively, a lot of IGM and CGM studies were done at redshift 2, 3, not at low redshifts. And the reason for that is this ability to do optical spectroscopy much better than UV. So here are some examples. So here are some examples of such spectra from this cross halo survey. So the black sort of shows the actual data. And then there are these theoretical fits of those absorption features. And these are various ions. So neutral hydrogen, silicon 3, silicon 2, silicon 3, silicon 4, oxygen 6. And there is a great diversity. The hydrogen absorption is the deepest, right? Because hydrogen is the most abundant element. So, you have many more atoms of hydrogen compared to other elements. So you get deeper absorption. Sometimes you have like many features, kinematic features of this absorbing gas. So you see, these are all within plus minus few hundred kilometer per second. And this is necessary because that's the only associated gas. So zero corresponds to the redshift of the galaxy to which you're associating this, CGM.
So, but if the hydrogen absorption is so deep and wide, then how do you even detect anything in that range?
You don't. I mean, right. No, okay, very good question.
The temperature is high.
No. The absorption wavelength are different, right?
But
So
here
they have put on the
they
same
have shown
velocity.
the same.
They have been placed on the same velocity. So they have been moved to the same redshift so that these line up. So this is not in velocity space, or the true velocity space. This is with respect to.
But you mean that they are observed as BLE? No.
No. Yeah.
Unless you see they also show up as BLE.
They would show up as DLAs, I believe. These are pretty strong absorbers.
They will have current density less than you got 24 or so.
No, 24, 21.
21, yeah.
Yes.
21, so.
That's correct. So these,
you mean these?
some of these definitely can be
So the
DLA.
galaxies have neutral hydrogen, pretty dense, that's giving the hydrogen absorption. But the CGM of the galaxies are hot and they are producing.
No. This is the CGM
But the
neutral
CGM
hydrogen.
itself
Also
has
has diffused neutral hydrogen. But perhaps not as much as the DLAs.
Yes, but the DLA is usually thought of as
The disk, ISF.
galactic disk itself has.
That's correct. Correct. But I mean, there are things like that it can also be CGM, which I have actually encountered, at least some claims. Now, so these would appear as lines at different rest wavelengths, right? So they are like easy to make. It's not that all the spectral absorptions will happen at this wavelength. They have just been put together here. Okay, good question. So this is sort of the observational summary. There is a volume filling hot phase, and the temperature scales with n to the 2/3. I think you know this as well. And most sidelines show absorption in a broad range of temperatures, from 10 to the 4 to 10 to the 6 Kelvin. So you have oxygen 6, silicon 4, and silicon 2, everything. Most sidelines. So now the question is how much mass there is across different temperatures, for example. How much mass there is of baryons in CGM from say 10 to the 4 to 10 to the 5, 10 to the 5 to 10 to the 6. And so that's a physics question, question based on physical properties. The other thing is this sort of multi-phase gas sort of is interspersed with the hot volume filling phase. So, the analogy of this is like our clouds, terrestrial clouds. You have clouds and then you have the atmosphere. So even in cloud proper, it's mostly air. The fraction of water vapor in a cloud is tiny, but it is able to produce a lot of scattering and absorption, even with tiny amount. So these are some of the big questions. What is the origin and sustenance of this multi-phase gas? Can we explain the observed columns, the covering fractions? That is, what fraction of the sidelines show absorption across different temperatures? What's the redshift evolution And what is the role of this diffuse gas in galaxy formation? As I mentioned to you, if you turn off any supply of gas in the Milky Way, you'll stop star formation in the Milky Way. So it plays an important role uh, in sustaining star formation. So, the mental picture that you can have for this multi-phase gas in the CGM is sort of like our terrestrial clouds, right? So you have clouds which have very little water vapor, yet it can cover almost the whole sky. Like, 50% of the atmosphere is covered. 50% of the area of the atmosphere is covered by clouds, which is sort of, you can say, multi-phase gas. And yet the volume fraction is like extremely tiny, or mass fraction is extremely tiny. So in the similar sense, the CGM clouds can be multi-phase, even if most of the mass is in the hot phase. So I think this is not only like a qualitative picture, it's also somewhat quantitatively correct picture to have. So this is something that we did. In fact, Alankar was also involved in this work. So to explain this multi-phase ness of the CGM, so this is Mukesh Bish, he is a PhD student at Raman Research Institute with Bhima Nath. And so we worked on this together. So what we have said is, okay, let's sort of just build an extremely phenomenological model of the CGM. What we say is that all the cool gas, you distribute it into spherical clouds. We don't even sort of forget about the complicated geometry and so on. Say if you have 10 to the 10 solar mass of cool gas, and if you're allowed to just put them in as this, so can you produce the statistics of covering fraction, for example? So, for example, this sight line will be empty. It will not show cool gas, but a lot of these sight lines will show absorption into cool gas.
So is there anything to do with the color code, or it's just, the spatial extent of each of the circles? What do they mean? Do they mean anything? No.
Basically, that's where the cool gas is sort of spread out. So this is a projected image. So you in 3D, they're sort of non-overlapping. If you project them, some of them are actually overlapping in the line of sight. So
these are gas particles, or
no. This is not a physical model. This is just like spatially, you're just putting these spheres. Okay. And this is how it will appear. So if you just ask what's the area covering fraction of this, it will be pretty high, because most of if you sort of shoot darts at this, a lot of them will hit some blue region, but some will not. So this is just a numerical, Monte Carlo realization of that. Now, why do we need to consider such a model? And the motivation for that is actually shown here. What is shown here is the column density, the inferred column density of magnesium 2, that is Mg plus, in this Gauss halo sample. So what you do is you try to look at presence of Mg2, you do the void profile fitting of that transition, and try to infer the column density. And what you see is that there's a large scatter in the column density. So these lower triangles are upper limits. So the actual thing is below this. These circles are detections, and these are lower limits. So the actual thing is above this. So you see, even at the same impact parameter, there is a great range in the value of column density. And that is what motivates this kind of picture. That is, sometimes you can have multiple spheres along the line of sight, sometimes you can have empty sight lines. These things may be empty sight lines. Okay.
But I think all of them are having similar temperature and density.
That's correct. So Mg2 is a tracer of 10 to the 4 in photoionization.
No, that circles.
That's correct. The spatial thing is that's correct. So
that's the power law thing that
these are like, if you spread it out perfectly smoothly, this is what you get. It sort of goes through the middle, but the scatter is true, right? The scatter is not like an observational, like an error bar. This is true scatter. So what it means is that, it's a picture like this. I mean, although what Somdeep is saying,
Observational data.
this is observational data.
So these are resolved impact parameters are also
Yeah,
captured.
yeah. I mean, you know how far is the galaxy.
That is very easy to do.
Yeah, that's an easy thing. This is very easy thing to measure. The hard thing is this void profile fitting and inferring the column density. Okay. So here is like an example of this numerical experiment and why this exercise is useful at all. So what is shown here is, so those blue circles that I just showed previously, we call cloud complexes. So all the cold gas is within those cloud complexes. So you can have 10 to the 10 solar mass of cool gas, 10 to the 4 Kelvin gas. You can spread that gas over a sphere of size RCC. So you can have like 1 kiloparsec radius sphere, 10 kiloparsec or 20 kiloparsec. You can put that gas into 100 cloud complexes, 1000 or 10 to the 4, right? And if you do this Monte Carlo realization of various things, so these circles, gray circles, are what the scatter plot will produce. So even if we are just assuming spherical and so on, but you can actually see that, for example, there are only out of 10 to the 4 Monte Carlo points, only 2 show very high column. So in this case, it was extreme. There are only 100 cloud complexes. And if you then have 10 to the 4 random dots shot, only 2 are detected. Because, the area covering fraction in this case is tiny. Right? So you do these experiments. For example, here, these are very big and very numerous. So there is no scatter between different sidelines. They're all overlapping. The scatter between these Monte Carlo points is small. So even this extremely simple non-physics model is useful to just give us a sense of what is sort of the size of this cool gas distribution. You would say, it would be somewhere,
So that's the size, I mean, each column.
yeah, so this is 1 kiloparsec size of blue. This is 10 kiloparsec and 20 kiloparsec of the blue. This is, so you have 10 to the 10 solar mass gas. Okay. So, and each of these 100 will have then 10 to the 8 solar mass. So each of them has a lot of mass, but there are only 100 of them. So the area covering fraction will be small. But if you hit one of them, the value that you get per column is high. But the probability of hitting is very, very small. So the area covering fraction here is small. Here, on the other hand, area covering fraction is unity, perfect. But the scatter between points is small. Right? So, this is just like almost an extremely toy model, but yet it has this power of just telling us, giving us a sense of what is the distribution of this cool gas in the CGM is.
These could have different column density.
These are column densities.
So that model with let's say left top corner.
Yeah, this one. So this is with 100 cloud complexes and 1 kiloparsec size.
So the column density range would be different.
Yeah. So the column. So this is observational data, right? It's common in all of them. This
Is your model.
green.
I understand, but
Yeah.
the range it should show. It will be smaller in this case.
Yeah, you see, it is small. The range of column densities.
Not range, actual value.
No, all of them have the same mass. The number of atoms of cool gas is the same in all of them. What you're saying is, if I put more cool gas or less cool gas, then
all of them are not showing a line of sight.
Yes.
Is it the mass of individual?
No, this is the total cool mass in the sea.
total cool mass.
Right.
You are dividing.
You're dividing this into 100 or 1000 or 10 to the 4.
Correct. And with the density as this number, that length scale is higher, the density should be lower.
No, I think.
The physical density is the same. The gas density in each of these is the same, but number of them is higher. So the number density of cloud complexes is higher. You understand? There are two densities. How many cloud complexes per unit volume?
The mass
That will
density
divide
is
by that 10 to the 4, 10 to the
Yes,
3 and
that's
that
correct.
number. But the density of each pair,
Mhm.
actual physical density of
That's
each
the
pair,
same. That has to be the same.
how you are dividing that by, let's say, 10 to the 4,
Yes, yes.
and
No,
your length scale is 1 kiloparsec or 10
see, the
kiloparsec.
thing is, again, I have to remind you of the cloud. Cloud is not all water. So if you have this cloud complex, I'm not saying that all of this is cool gas. It's made up of a lot of cool gas, which is tiny, but not all the mass in this sphere is in the cool gas. There's a lot of volume which is just hot gas.
Pratik, just one clarification, the RCC is the size of the cloud patch, or I mean size of.
This is RCC.
This is
And
RCC.
you can think of this as sort of composed of a lot of tiny
We
droplets.
actually had a picture.
Yes, yeah. Actually, yeah. Zoomed in picture. This one. So if you zoom in on each of this is how it looks like. So it's not gas at very high physical density. There's a lot of air in between.
Maybe then, if I understand Shomadip's question, if you go to the next slide, think if it's RCC is 1 kiloparsec versus 10 kiloparsec, and you have, yes, you still have the
100 clouds. In all of these, we have 100 clouds.
100 clouds, and this
So-
is 10.
And so each cloud will have 10 to the 9 solar mass of cool.
10 to the 8.
8.
So each of these
10
will have 10 to the
solar
8
mass
solar
of
mass.
So then the density, so then you have total of 10 to the 10 solar
That's
mass,
correct.
right?
Yes.
And
And
then
even
in a 1 kiloparsec type of region versus a 10 kiloparsec
10
versus a 20
kiloparsec,
kiloparsec.
So if you spread the same mass in 10 kiloparsec, there's a lot of hot gas in that
Oh,
cloud
so
complex.
that's the idea.
That sort of is the idea, right? That
So the idea is
This-
that not this is fully filled.
it's not fully filled with only coal gas. It has a lot of just like our terrestrial clouds, right? It sort of has a lot of air, not just water droplets. That's correct. That's correct.
Bigger volumes.
That's correct.
That doesn't mean that it is the only
That's
constituent
correct.
there.
That's correct. So it's just cool gas is only spread out till that radius. That's correct. Yeah, this is an important thing that I should have emphasized, but it's good that you brought this up because it's important. Otherwise, you would think that
Yeah.
same mass, how can you expand it to such a big volume? Okay, cool. Now, coming back to physics, I'm already an hour into the talk. But so that was really not physics. Now we are moving a little bit into the physics part. So now, how do you produce this long-lived cold gas along most sight lines? So, because naively speaking, you would think that even if you have dense cool gas and if it is moving through hot phase, it will get mixed and it will just evaporate. Now, a realization in past 10 years or so is that radiative cooling fundamentally changes the nature of mixing. Okay, so some of this stuff is like classic stuff on how baryons accrete onto galaxies. So this is the famous cold mode, hot mode picture. That is, if you are in massive systems like clusters, most of the baryons undergo a virial shock. They get heated to the virial temperature, and the innermost part can cool. But if you go to lower and lower mass halos, around the Milky Way mass, you transition to something called a cold mode, in which this material that comes in, the cold material that comes in, does not really undergo a shock. Without getting shocked, it just falls directly close to the galaxy. So this is cold mode, and it's this is like a early simulation of this. This shows all the baryons. This shows only cold baryons at redshift 1. I've also done some work on this cold gas production in the galaxy cluster, something called precipitation model, that if you have heating and cooling in a diffuse atmosphere, if you're in the right parameter regime, that is, if your radiative cooling time is short enough, you can actually condense cold gas from the hot gas itself. As I mentioned, I think perhaps I didn't emphasize much, most of the mass and most of the volume is in the diffuse gas, in the diffuse hot gas, not in the cold gas. It's only the area that you have very large area in the diffuse gas. Now, these are other observational examples. If you look at some of the cluster galaxies, they show these spectacular tails in multi-wavelength. So here is such a galaxy called a jellyfish galaxy. And what you see here is in H alpha. So this is 10 to the 4 Kelvin cool gas. And then these things are surrounded by soft X-ray emitting, somewhat dense plasma. So these are galaxies moving through galaxy clusters, and the gas of these galaxies, the circumgalactic medium and the interstellar medium of these galaxies are sort of drawn into these spectacular tails. Okay, so these are some of the ways in which you can sustain cool gas.
Just a clarification, that lens school is 10 kilopascal.
This one?
No, that observation.
Yeah, this is 10 kiloparsec. So these can actually be like 50, 60 kiloparsec long tails, which is actually amazing, right? Yeah. So there has been like some recent work of the theoretical kind where you have cold, dense gas and you have wind blowing in it, and you form these kind of tails. And in fact, instead of getting mixed up, this cloud produces a lot of mixed gas, which is at intermediate temperatures. And as I showed you that cooling curve, the gas at intermediate temperatures has a very large lambda. That is, it's very efficiently cooling. So all this gas can easily cool in the tail. And in fact, instead of evaporating, you can get more and more cool gas mass condensed in these tails. So some of this work is actually also done by Alanka. So I'm actually going to talk about a recent thing that we did. So there are cosmological simulations which are like extremely popular, and like Illustris, TNG, and all these, but they are limited in the sense of resolution. They really do not have resolution to capture some of the physical baryonic aspects. For example, radiative cooling, turbulent mixing, and so on. So there is a need for more focused simulations for really like just isolating the physics of certain important processes. So one of such idealized model is something called this turbulent radiative mixing layers. So the problem, have you done fluid dynamics? You have done fluid dynamics.
Very lately.
Okay.
Just part of it is small.
Okay. I mean, by the way, Arnav Rai Chaudhary's book is really, really, really good. It's very well written. And I'm not saying because I'm his colleague. I'm saying because it is actually a good book. That man has a knack for writing well. So you should read. Even his popular stuff is extremely well written. He knows how to convey maximum with minimum number of words. So that's an art you should also try to emulate. So here, his book is actually his book is a really good book for covering the astrophysical fluid, basics. Okay, so here is a simple fluid setup in which you have a dense phase and a diffuse phase, and there's shear between it, and there's like a step, a jump. So the velocity and density both jump there. So if you have such a system, this interface is unstable to Kelvin-Helmholtz instability. So the instability grows here, and it can become nonlinear and so on. And it will form a lot of mixed gas, okay, which will have properties in between this and this. And that mixing layer will actually grow. But so this is in absence of radiative cooling. This is the classic problem that has been studied. But if you have radiative cooling included, the nature of this evolution changes fundamentally. If you have radiative cooling, what happens is there's mixing, but it does not grow. It reaches a steady state in which there is a balance between turbulent mixing and radiative cooling. The two sort of counter oppose each other and reach some sort of an equilibrium. So, so now I'll actually show you a movie of that evolution of this Kelvin-Helmholtz instability without radiative cooling. So I already mentioned to you what the setup was. So these are all called free shear layers. You can sort of imagine like the ocean and the wind blowing, right? So high density and the wind. Forget about gravity for now. I mean, I'm not saying gravity is not important. Let's just go one by one. So how does it evolve? So I'll just show you a movie. So what is happening is this stuff. I mean, the late times, ignore the late times. Late times, the boundaries, this big stuff touched the boundary and there was something. But what you see generally is that this layer becomes Kelvin-Helmholtz unstable. It breaks into turbulence, and this turbulence sort of spreads more into the diffuse space and not so much into the dense space. Okay, this is the evolution without radiative cooling. This is well known. In fact, this is actually like a very nice fluid dynamics problem. So you all have done Sether-Taylor blast wave, right? Sether-Taylor. Supernova, if you have a point explosion in a medium, there is a classic.
Some of them have.
Okay, so you have not seen R going like E T squared by rho to the 1/5.
Yeah.
I think the person working on jets
So yeah, Ankit has.
must know this because this is related to that. Ankit must know this because then this becomes LTQ. So this is basically.
Dimensional.
I just make clarification around your last slide. For the Kelvin-Helmholtz instability, you need to define directional.
Yeah, so there is a shear flow.
And the densities must be different. but
No, not necessarily. Density need not be different.
they
You can have Kelvin-Helmholtz even with the same density.
But is there any difference that I have to have in those two layers?
The velocity.
The velocity is just opposite, or the values of those two?
Different.
They should just be different, right?
Just
Yeah. If they didn't see, if you go in a bus which is moving very, very fast relative to this, the evolution will be the same, right? This is Galilean invariance applies to it. Right? The frame translation does not matter. What matters is the relative velocity between these two layers. So in this problem, these are the parameters of the problem. Velocity difference between two layers, the pressure of, I mean, the two are in pressure equilibrium, the density and the density contrast. That's it. There is no other parameter that characterizes this problem. Out of these things, you cannot create a length scale by dimensional analysis, right? So the length scale can only occur through an explicit time dimension. So delta U times T is the length scale. Similarly, out of E and rho, you cannot create a length scale. You create a length scale by introducing T there in the Sether-Taylor solution. So here, the length scale is just delta U times T. So what it means is that this discontinuity will evolve self-similarly in time. And this is the demonstration of that. The x-axis, so these are different panels for density, uniformly spaced in time. And what you see, this is the average profile and 1 sigma variation of density, right? You have this mixed stuff. So you have average density and there's a large range of density at every height. And so what you see, this spread out thing is basically where you have turbulence. And what you see is that the boundary of this thing is almost uniformly spreading with a constant velocity. Similarly, in the dense part, it's uniformly spreading. So it sort of satisfies this self-similar evolution. Okay, so now let's go to the real problem. If you have radiative cooling, what happens? So let me just show you the movie. Okay. It's the same setup, but now we have radiative cooling in there. And what you're seeing is that this Kelvin-Helmholtz rolls form, and instead of just growing and filling this up, it actually reaches a quasi-steady state, right? You see a qualitative difference between this movie and the movie that I showed previously, and the only difference here is the radiative cooling. So what happens is there is this Kelvin-Helmholtz instability which produces mixed gas. That mixed gas has a short cooling time because your cooling function had all these peaks and so on. So that gas is very radiative. It does not like to be there. It sort of quickly cools. So what happens is there's a competition between production of mixed gas and condensation of mixed gas. So cool gas is produced because of the mixed gas is produced because of Kelvin-Helmholtz. It cools and just sort of settles onto this. So the mass in the dense phase actually increases. So this is a way in which you can sustain and actually grow cool gas that you need to explain the ubiquitous multi-phase gas in observations, for example. And if you look at the cooling time, so the cooling time here is long, cooling time here is long. This at the interface is where the cooling time is short. So if you look at the cooling time snapshot, it has a fractal-like behavior. And people have tried to characterize it. But the overall thing is you're able to entrain a lot of diffuse hot gas into the cool gas.
What was the density contrast?
In this case, it was 100. So 10 to the 4 and 10 to the 6. So that's the temperature contrast, and it's almost in pressure equilibrium. So the density contrast is also 100. So 10 to the.
Good. No, I'm saying what kind of cooling processes are.
Right. So the cooling function that I have included, that's exactly what is included here. So it has line cooling, Bremsstrahlung, cooling table. Basically, it uses the cooling table, solar metricity. But it's as long as the mixed gas has a short cooling time, this behavior is universal.
It's also not the density contrast, but the actual density. Right?
That's correct. So the actual, as long as the cooling time of this stuff is short,
Shorter than this,
then the two things you'll have this behavior.
But to have the cooling time shorter, you should have the density in certain.
Yeah, that's correct. So the things that you sort of keep in mind is that the density is say 0.1 and 10 to the minus 3 for the cold and hot phases, or 0.01 and 10 to the minus 4. So these are typical CGM numbers. Okay, so actually we have this paper recently, and we have done some sort of turbulence analysis of these turbulent radiative mixing layers.
So is it public, the TRML code?
The code,
The TRML, that's not a public available thing.
the code, I mean, the code that we're using is something called Athena K. Athena K, so it's sort of Athena plus plus and so on. The code is not really code is public, it's an open source code. Our implementation and so on is what we have done. An analysis, actually.
No,
This
I
kind.
understand. It's like to.
Yeah, it's sort of
in
like.
that case, like
That's correct. That's correct. Yeah, we have just set this up and tried to.
Calling that
This
particular
setup,
thing that
this setup is TRML, like Kelvin-Helmholtz. So turbulent radiative mixing layer. So it's turbulent. Turbulence is extremely radiative is extremely important. It's mixing layer. It's basically TRML. Okay, now we have actually done we have actually done something called Reynolds analysis. So this is a classic fluids technique in which you can quantify turbulent transport using averaging. And so to give you a flavor, you've also done the Shakura-Sunyaev disk, alpha disk model a little bit. So that also, the classic problem in accretion is that the molecular viscosity is so small that the viscous accretion time is just too long. So you need the disk to break into turbulence, and you need enhanced transport of angular momentum due to turbulence. So it's a similar thing. So what we have done is we have analyzed these correlations between, say, density and velocity. So for example, if you look at the mass conservation equation the system that we have is translationally invariant, right? So, this position, this position, this position is all uniform. This direction is also symmetric, right? There's nothing to pick out, but the vertical direction is not. There is a definite place where things are happening. So what you can do is you can analyze this only as a function of z. Okay, so you can average this in this and this direction, and you just get 1D equation. Okay, so if you have this equation, it just becomes dou z of rho u z, and these angular brackets just mean an ensemble average or horizontal plus time average. So you can actually write rho u z as this plus this. Okay, so these are turbulent fluctuations, turbulent correlations, so higher density and positive velocity fluctuations. If they're correlated, it can give you turbulent mass transport. If this correlation is zero, then you don't get mass transport. But if there is a positive or a negative correlation, you can get mass transport due to turbulence from hot to cold or vice versa, depending on the sign of this. So what we have done is we have analyzed our simulations using this kind of analysis, and this is called Reynolds averaging. Okay. So I don't think you have done like this much fluids, but it's actually really, really fascinating. In fact, the person after whom Reynolds number is named, Osborne Reynolds, was the one who actually applied it in incompressible flows in 1896. So, it's more than 100-year-old technique in classic fluids. We have applied it to extremely compressive flows. In fluids literature, this is extremely common. And it's an extremely compressible flow, but isobaric. So if you look at first law of thermodynamics, which is sort of shown here, this is a specific form of the first law of thermodynamics. So the density can change either due to pressure change or due to entropy change. Normally, when we're doing sound waves, for example, we just sort of take the process to be adiabatic, and the density change is brought about by the pressure. But in the present case, the radiator cooling is more important to drive the density change. And you can sort of ignore this. So it's almost isobaric, but the density change happens because of radiative losses. That's the entropy term. Okay, so this is a regime which the engineers have not really studied all that much. Engineers have studied fast supersonic jets and all that. So this is extremely important. So density changes are produced by pressure changes by supersonic flows. But this regime is not that well studied. Okay, so this is like an example of these turbulent correlations. And you see they are definitely non-zero and they're not just random. There is definite turbulent correlation. Similarly, so I just showed you the example of mass, turbulent transport of mass, but this is the transport of X momentum. So for example, if you have a flow in a pipe, if the velocity of that flow is small, the pipe sort of experiences viscous drag, and that's due to molecular viscosity. But if the velocity of the flow increases, the flow in the pipe becomes turbulent, and suddenly the drag on the pipe increases. Okay, and that's because of this kind of transport of momentum due to turbulence. So turbulence is a great way to enhance transport of mass, momentum, energy, whatever, right? And it's a fundamental process. So we have actually characterized the mass transport, X momentum along the shear direction transport, in the vertical direction momentum transport, and the total energy. Okay, so it's somewhat technical, so I'm actually just gonna skip, but I want to emphasize this. This is the energy budget. So this line is just n squared lambda dz, cumulative radiative losses till that height. So you start from the bottom, there's no cooling till you reach the TRML where the mixing happens. There you have a lot of cooling, and then you enter the hot phase, there's not much cooling there. So all the cooling is here. So cooling is actually balanced by enthalpy flux. So there is flux of pressure, internal energy, enthalpy, which comes from the top. And that is what balances this radiative cooling. and this reaches a steady state, right? I showed you in absence of radiative cooling, this mixing layer just grows linearly with time. But with cooling, it reaches a steady state. And we have sort of, this is sort of the balance of this steady state. So it's a little, dense stuff. So if you're interested, you should check out that paper. So basically, this is one idealized problem. We have also looked at simulations of clouds moving through the diffuse medium. So this is like Alankar's work. And this is just a visual. In fact, Alankar did this visualization. And what you're seeing is like if you have a cloud and you see these turbulent, fractal looking surfaces where a lot of cooling happens, what you're seeing is actually a map of cooling time. And this is transparency. So if you have gas which is very, very hot, this medium is totally transparent. So what you see is that you're looking through. So this is like a 3D volume, but this is called volume rendering. So you're looking through a lot of diffuse gas, but you're sort of seeing this intermediate mixed gas. Similarly, we have studied multi-phase turbulence with cooling. So these are all idealized. This is the kind of stuff that I really like. That is more physicsy, but relevant to astrophysics. So here we have interplay between turbulence and radiative cooling, and how does the nature of turbulence change if you have radiative cooling. So I'm not going to go in details. They're already a lot over time. So this is sort of my summary. Okay. So the multi-phase gas is ubiquitous in the CGM. Most sightlines encounter a range of gas temperatures. We see this from quasar absorption line studies. Now, how do we model it? So I showed you this misty cloud complexes model that Mukesh Bish was modeling, and also Alankar in this one. So these cloud complexes can cover a large area with a small volume / mass in the full phase. Then I talked about physical models, so not so much about these two, but I just gave a snapshot each from cloud crashing and multi-phase turbulence. I talked a little bit about this TRMS, turbulent radiative mixing layers, these interfaces between dense and diffuse phases. So the upshot is that the cooling time should be short. And we know that the cooling time for the intermediate gas, mixed gas, is short. So this is a necessary condition, but this condition is satisfied in a lot of the systems that we study. Now, a big question is, so we understand this physics more or less, how do we incorporate this physics in cosmological simulations, which are by necessity low resolution, right? The simulations that I was showing, the box size is 10 parsec, and there are like 1,000 grid cells. So it's sort of like 0.01 parsec resolution. You cannot do cosmological simulations with that resolution. But is there a way to just sort of incorporate modeling of this in large-scale cosmological systems? That's like a big question. A lot of people are trying to do that. People are trying to also use machine learning or whatever to do this. But that's the next frontier in cosmological simulations. So with this, I'll thank you, and I'm really sorry for exceeding the time.
Okay, questions?
Yes.
Yes, sorry.
So I was thinking that on the CGM, in the very beginning of slides, you have shown that baryonic gas enters the halo and sometimes reaches the galaxy and there are outflows. Now these baryonic gases obviously increase the star formation.
Yes.
So is there any fundamental difference between CGM around elliptical and spiral galaxies because the star formation is different?
No, that's actually a very good question. And so the elliptical galaxies do not generally show so much cool gas, whereas spiral galaxies do show somewhat more cool gas around it. But the large scale CGM properties are not very, very different because the CGM extends to till 200 kiloparsec. In the nearby regions, there are differences. But on the large scales, for the same halo mass, there are not many differences. For example, one of the early cos halos papers was this oxygen 6 absorption. So they showed that oxygen 6 is predominantly in star forming galaxies. But I'm not sure if that is because of like a halo mass, because we also know that more massive halos have lower SFR. So it can also be a fact because of the halo mass dependence that star forming galaxies are showing more oxygen 6.
Yeah, I guess star formation in the galaxy is influenced by multiple processes. So your point is very good that does it mean that the CDM is different or not? It could be because the whole environments are different for spirals and VFWs. But then also there are internal processes, astrophysical processes that can affect star formation itself.
Okay, other questions?
So I want to ask this comment because eventually, so the last big question that you are talking about, I mean, eventually for all the things that are done, I mean, the entire phenomenon of subgrid physics in cosmological
Is
systems,
sort of
that's
this kind
from
of
here.
absolutely.
You have to have some way
Yes.
extrapolate. I mean, unless you cannot go to that.
Yeah, you cannot like simulate star formation
Yeah,
from first principles, but you have to put it
star
in
formation. Cannot simulate black
AGN
holes.
feedback. Yeah.
Even if you knew about physically
Yes.
how black holes
That's-
come, how
that's
sick
correct.
black holes are formed, then also you cannot do it.
Right.
So I think the major thing that people try to do, which is often very criticized, is that they try to extrapolate things. That suppose the physical conditions at a scale, let's say a parsec scale,
Much larger scale,
parsec scale, how could that scale, roughly how can you scale them to a scale of kiloparsecs?
That's right. So there's a lot happening even in that. Like how do you implement like AGN jets in the best possible
Yes,
way
but
in these simulations?
I think ML, as you say, machine learning, that is a very good frontier.
Right. That's
So they
something
can
is a
do a
lot.
lot of these scalings very quickly and have multiple versions
That's
of the
right.
simulation. Like some of our students are using the ML simulation to do something like that.
That's right. That's right. So that's like you have a bunch of simulations with
Yeah,
different
and you scalings, you can do
feedback.
scalings.
And then you want to ask, oh, if I had run Simba with
Yeah.
these
This-
parameters, what would I get?
Right, that's
So
right.
that's sort of like a
Computational thing. That's-
interpolation kind
interpolation,
of
that's
this.
interpolation.
Yeah.
Sometimes you can call it extrapolation.
Yeah.
Often extrapolation also. Yes, interpolation. Anirban was also doing something.
Yeah, so my question was regarding that plot where it was the impact parameter versus the MG2 pattern. So what I understand is, so these are galaxies of around redshift 2.
No, these are like low redshift galaxies.
Okay.
Like our neighborhood essentially.
So